All right, so let's go to the whiteboard. So one of them should be easier than the other, right? So let's use another color for this. Use blue. All right, so if it goes in that direction, right, it slides, then it probably slides in reverse, right? Yeah. So then Ri would be what? Li plus 1, right? You guys see that? Makes sense? So it just slides kind of like that. Now, the other one, we know that to get to this one, we need this one, right? This Ri plus 1. So then we've got Ri plus 1, and that would get XORed with something to give us that one, right? So what this is where it's probably a little bit confusing, right? So how does that work? Now the function is there, right? So it's the same function fi plus 1, but that function takes an input, which is Ri, to go through here, and we don't have Ri, right? However, we know that Ri is Li plus 1. So then basically it's Li plus 1, like that. Do you guys see that? So that's kind of the idea. So Ri is Li plus 1, and then Li is Ri plus 1 XOR Fi plus 1, Li plus 1. Make sense? Any questions? Right. So anyway, so this is just what's the point of the exercise, to kind of think about what's going on, the relationship. But basically, DES, all it's doing is, if you notice, it takes a block, splits it in half, and it starts moving them around, right? And it takes usually a block, runs it through a function, and produces another block, right? And that's really the logic that you have in DES. So it's nothing more than moving things around and doing XOR operations. Okay, so let's kind of complete the last part of DES, which is to look at the F functions, right? So these F functions do something, which is basically take an input block of a certain size and produce an output block of a certain size. Okay, so we're going to explore that last part, but you will see that it's very similar. Okay, so we're going to talk about the functions now of DES. So the functions, okay, these F functions, F. Okay, so the idea with the F functions is you start with a block that, let's say, is 32 bits. So a 32-bit block, and this is the block in question. And then you have a key, and the key is actually 48 bits. Okay, so it's a little bit longer, right? And so what happens in the algorithm is that the 32-bit is padded, basically. It's incremented, and this can, vary, but it becomes 48 bits. Okay. And then once you have two blocks, the information, the actual, let's say, original plain text that's being modified, it gets expanded by padding. It can also be shifting, replicating the bits, etc., as long as you're consistent, right? And then these two, as you might imagine, get XORed, okay? And with the key. And remember, this is in the functions, right? This is in the functions. So if you notice in the Feistel network before, we were not using a key, right? The key is being used in these F functions here, okay? So we go back here. This produces a block that is 48 bits, okay? 48 bits. And then the last part of this is to do something called the S boxes, sorry. So that's the last part of it. So now I'm going to go over here. You have a 48-bit block, and 48 is divided by 8. It's divided by 6. Yeah. So it's gonna be 8 blocks of 6 bits each, right? So we're gonna do this, and this is the end of it. So you go over here, you've got 6 bits, 6 bits, 6 bits, and the final ... 6 bits. So you're literally, once again, breaking the block here, the 48-bit block, into how many smaller blocks? 8 of size 6 bits. And then these blocks go through what are called the S boxes. So you're going to have S1, S2, S3, all the way to S8, right? So if, you know, and now these S boxes, what they do is they take blocks that are of size 6 bits and produce blocks of size 4 bits, okay? And that's your encryption. So this will produce 4 bits each. See that? 4 bits, 4 bits, 4 bits, 4 bits. And this is the final output, which would be how much? 32 bits, right? So this is going to be 32 bits, and it's the original block that you start, or the original block size that you started with. So these S functions are based on it's the final part. These S boxes are based on a table lookup, okay? And so they're really like a type of a dictionary that you have available. All right, so let's define the S boxes. Okay, so S boxes are functions that take a sequence of bits of size 6 and produce a sequence of bits of size 4. Okay, let me do that. So 6 bits. All right, so we're going to do an example of how they work. Okay, so sample. All right, so you're going to have sequences of bits, right? You're going to have 6, let's say it's something like that, right? And the output has to be something like that, right? So a sequence of 6 bits becomes a sequence of 4 bits. So this last part is done through these S boxes, and it should work something like this. Okay. And then over here. Okay. So the top part is called the middle 4 bits. So middle 4 bits, the column part, and then the row part is called the outer bits. Okay, so given this, so let's say that your input, oh, and then there's got to be a mapping here. So let me just make these a little less crowded. So this is, as I said, it's a lookup table. Okay, so should be. All right, so 1101 0011 0000 1110 1 0, 0, 1, 1, 0, 0, 0. Gonna do the last two. That's 0, 1, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 0, 0, and 0, 1, 0, 0. All right, so given the input 0, 1, 1, 0, 1, 1, what is the output given these S boxes? So that's the S box, right? A sequence of 6 bits goes into the S box. The S box is nothing more than a lookup table, this one. And you specify that you have the middle 4 bits and then the outer bits over here. So by using this information, you can look up the mapping to the 4-bit sequence. So which one of these would you say it is for this one? So what are the outer bits? These two, right? And what are the middle bits? These 4. Okay, so if we do the lookup, 11's, 1101, that's that, right? And then if we do the outer bits, it would be these 2, right? So then what's the conversion there? Should be this one, right? So 1, 0, 1, 1. And so the S box would produce 1, 0, 0. Do you see that? And that's it. That's literally the data encryption standard algorithm. It's complicated, but at the same time, there's some simplicity to it, right? It's got like 3 ideas: XOR, right? The Feistel network that you guys saw, these F functions that happen in the Feistel network where the key is used, right? So you can go back. Right? That we defined over here. Remember, this is where you XOR the block with the key, and then that final 48-bit one, it gets broken up into blocks of 6 bits. They go through the S functions, and they produce blocks of 4 bits that get rearranged together to produce the final block using these S tables, basically. And that's it. That is the data encryption standard. What do you guys think? Love it? Do you want to implement it in a homework assignment? No, right? Yeah, so imagine now AES. And this is my point with the algorithms, right? So AES is even a little bit more complex, but at the end of the day, it's a lot of scrambling and things like that. RSA is not like this. RSA is like more math, but it's like algebra. Like when you took your algebra class, it's different in the way that it works. And RSA, remember, is what we're going to use to transmit the key. All right. But this approach, data encryption standard and AES is the algorithm that is used for symmetric key encryption. And this should give you at least some insight into how the algorithm works. Yes, go ahead, please.
So it's always going to break it down to 6 bits. Otherwise, it can't use the S box, right?
Yes, exactly. So if you have those tables are created by people doing research, right? It's possible that they could create something similar where the inputs are 8 bits and it produces 4 bits. This can change, and this is where you go from like Blowfish 1 to something else, right? But the idea is that you're basically just always converting blocks in some scheme to other blocks. And sometimes they're the same size, sometimes they are not. Okay, guys? So that's the data encryption standard, and that's the algorithm. So I usually do not go as far as coding this one, but we will code the CBC algorithm. Okay? Any questions before we move on? Everything clear? So there will be some questions about this on the exam, right? So remember, what are the possible questions? What are the 3 key ideas of the data encryption standard? So XORing, the Feistel network. What else? The functions, right, that do the mapping, the S boxes. the end of the day, you're just scrambling things a little bit, moving the blocks around. And yeah, that's kind of it. AES, of course, is a little bit more advanced, but that algorithm we are not going to cover in the course. All right. Okay, so great. So the next thing we're going to talk about, we're almost done for today. So I guess I'll just leave the rest of the time if you guys have questions for the exam. So I'll stay in, but I don't want to give you another new lab assignment. So let's go ahead and talk a little bit about triple DES. All right. So why, as the name implies, the idea so let's talk about triple DES. You have to kind of understand the context of what happened with DES. So DES was broken in around 1997, we said, by exhaustive key search. So it's like a dictionary attack, right? So that takes time to accomplish, right? So they measured how long it was taking, and basically they just said, okay, if it takes so much to break DES once, let's just use DES 3 times, and it'll take 3 times as long. You see that? But obviously that's not how it was intended to be used. And so it was inefficient. It was slow. It was slowing things down, but it's kind of like a temporary thing until the AES standard was made available. Okay. But let's just talk briefly about triple DES and give the formalization of it. Obviously, the algorithm is exactly the same. It's just that you're performing this 3 times. So it's called triple DES. Okay, triple DES. And the idea is basically that you're going to perform 3 encryptions using 3 keys, obviously, right? So it makes kind of no sense to use the same key 3 times, right? Because once they break 1 key, they would break all 3. Instead, you want to have 3 keys so that they break 1 and then they still have to break the other 2 keys, and it's not so straightforward. And it may not be a linear time that it takes to break it, right? Because, it's a little bit harder. So given the message here, okay, and that's the basic algorithm. Now, the procedure would be, as you might imagine, something as you encrypt the message once with key 3, and that's the message, right? And that produces a new cipher, correct? That's going to be like cipher step 1. And then that cipher gets encrypted with the next key, key 2, right? And this could be, really, it could be a decryption 2 or an encryption, just another step in the process. And then this produces a cipher, correct? And so then you can do the last part, which is going to be key 1 over here. I think I got all the parentheses correctly. Yeah. And that's basically triple DES. Just like that. I mean, that's the formalization of it. So it's meant to be slower. Okay. Now, I think in the slides, I already talked a little bit about AES. I'm not going to get, as I said, it's a little bit too complicated to talk about AES. But let me just, and like I said, it uses matrix multiplications for a lot of the operations to be much more efficient, okay, like linear algebra. So DES was too slow, but in sometime in 2000, we got the advanced encryption standard. And this, as I said, is the standard being used today. The advanced encryption standard. Okay, the key is bigger in this one. It's fast. It's a fast algorithm. It's more secure. It hasn't been broken yet. Yeah, so that's basically where you kind of are in the state of the art. Right, so that concludes basically symmetric encryptions. The next thing that I usually do here would be to just do the last homework assignment, which is to implement the code for CBC, but I'm going to hold off on that one for after the exam next Thursday. That will be your lab assignment, and that one will be due a week from Thursday. I believe I graded all your homework assignments, I want to say. Except